All right, let's do our income and age problem. This was our table of data. And so we got some probability related to that and our categorical data. We're going to have a graph with it. So let's take a look. Here we go. So we have the annual income, and you were in an income category and you were in an age category. So we had two variables there. So what's probably the person chosen at random? So that's out of all of them. Was will be in the 31 to 45. So that's of course your 89 out of the total 207. So there is that. The probability of being in that out of the sample that they chose, which I bet was just this. Yep, a simple random sample. So one sample, you picked a person out and you said, okay, what age category are you in, and what income bracket are you in, and then you put them in that part of the matrix. Okay, so that's what's happening with this two-way table. But next, we say, what's the probability that a person chosen at random from those in this sample whose income are over 50,000? That is the given that. So, given that you make out over $50,000, that means I am only talking about these numbers here. So out of those 96 people making over $50,000, what proportion are the 31 and to 45-year-olds? So they have to be that intersection of that 31 to 45-year-olds in that group. So it's the intersection of those two uh, qualities, those two variables, out of the total 96. And that is 0.36. So, in essence, what that is saying, overall in my sample, 43% were the age 31 to 45. But if I knew you were making over $50,000, then only 36% of that category, that income bracket, was in that age group. So, what do you notice about these two things here? I notice that they are not the same. I notice that, if I know that I am just looking at this over $50,000 category, then it has now made less the probability that you're a 31 to 45-year-old. Okay? So that's where that falls here. So, based on your answers in part A, are they independent for those in the sample, and explain? So, I wanted to check and see. So, you had to reference your answers in part A and part B together to discuss that. And so I did. I showed that no, 0.43 and 0.36 are not the same. The fact that you make over 50,000 makes it less likely that you are in the age category 31 to 45. And then I stated, of course, those two percentages. So that's what we were looking. Do you remember that for the independents, we're looking to see if the probability of A overall is the same as the probability of A given B. Okay, and then that's what this format was here. All right, next you're asked to graph. Make a graphical display. So I need to make a graphical display that's categorical. Okay, and so that means it's a bar chart. That's a categorical pie chart. But with pie chart, I wouldn't be able to display multiple age categories. I would just say be able to do one age category. So in this case, to do multiple age categories and the multiple um, multiple incomes, then I had to do this segmented or stacked, whichever way you drew it, and you could do it this other way, like this way, sideways, or whatever. Uh, you can do it stacked, and so turn this whole thing on its side and do it that way. Okay, you could have also categorized it by you could have done the bars with the income and done the three bars of income, and then in the income, you would have four colors of the age. But the point is, I expect to see labels, okay, on both of the axes. I also expect to see this done in percentages. okay? Because it is not really plausible for me to be comparing groups that have anywhere from 89 to 15 in them, without making them into percentages. So I first decided and I made them into percentages. So 8 out of 50 was 16%, and so on. So I made the percentages, and then that's where I got all of those numbers in there. So labels, some kind of segmented or stacked bar graph, and percentages. All right, next, if we were going to do an inference procedure, hopefully you recognize one sample, two variables. This would have been a chi-squared test of independence. And then look here, if age and income were completely independent, then how many would you expect? So that's the expected count. So I want to do the row total times column total over total for that 46 to 60-year-olds in that income over 50,000. So I went up here to the over 50,000 and the for this box here. So I did 53 times 96 divided by 207. All right, and that's what was expected there. Very good. So now, our second word problem on this day that we had done our work was this bauxite ore cars. So this one has to do with the normal model probability, okay, but also sampling distributions. So you're going to see as we progress through this page that we're not just talking about the probability of finding one randomly selected car, but we'll come down here and we'll talk about the probability of finding a sample of 10 that have an average of something, a sample mean, not one. And then even at the end, it talks about having a sample of 40 that has a sample mean of something. So that's what you're watching for when you're doing these normal model probabilities. Is it one where I'm using this population standard deviation? Or is it a sampling distribution where, look, I have changed the standard deviation because it's for samples of size 10? All right, so quickly you can see our z-score. We have our x minus the mean over the standard deviation, and then we got the probability by doing our norm CDF. So see, in fact, I think I have a picture of it down here in part E. You can see the sketch of part A. Okay, I might should have labeled that a little better, of course, with our mean of 70 and so on. All right. And so that was our 21.8% chance. So that's not very unusual at all. So a couple of ways you could have supported question B. No, it's not unusual because it's not even one standard deviation away from the mean. Also, there's a 21.8% chance of getting that sample or something more extreme if 70 is the center. Not unusual at all. So I would not, that could just be sampling variability. See that idea of that p-value kind of idea. All right. Now comes samples of size 10. That now makes a sampling distribution. So it is not just individual cars, it is an average of 10 cars, an average of 10 cars, an average of 10 cars, averages of 10 cars. Well, what does that do? That has now changed the standard deviation for this to be the zero 0.9 over the square root of n, square root of your sample size. So the variability has now changed because the samples to samples are now being more closely clustered around the mean. So see, now we are 2.4, an average of 10 cars being 70.7, not just one single car being 70.7, but an average of 10 cars being 70.7 is now 2.46 standard deviations above the mean. That's now getting quite rare. In fact, look at that probability of getting that or something more extreme. So, absolutely, yes, that is definitely unusual to get an average of 10 cars at that point because that's almost 2.5 standard deviations above the mean. There's less than a 1% chance of getting that sample mean if the if the machine is filling to an average of 70. So something's happening, I believe. All right, there was the sketch. Now, given the initial mean and standard deviation, I like that they tell us back to that again. So, given the initial mean and standard deviation, how full are the most heavy 10% of the cars? So, if you're wanting to kind of see a picture of where we're talking about, how much do these cars weigh? The top 10%. So, I need to get a z score at that spot. And so, I'm going to do inverse norm of that 10, that zero point 0.9, that 90% below that spot. So the z-score is 1.28. So there it is. And there's my x minus the mean over the standard deviation. Make sure you are showing your z-score formulas with the z equals. Do not make these naked x minus means over standard deviations without the z equals, because by you putting z equals, you're indicating normal model, not t-distribution. Okay, that you are doing normal model math. And we can do that here because look, we were told the population standard deviation. So z scores apply on this page. Z scores apply on this page. All right. So now, so that made it a 71.15 ton coal car in the top 10%. Describe the sampling distribution. Describe the distribution. That's your socks. Shape and outlier. So that's approximately normal because the population was approximately normal. The center is a mean of 70 and the spread is a standard deviation of 0.28. 285. See, it said of the samples of size 10. So I was referencing this here. Okay. All right. And then finally, what if we did samples of 40? What would that change about that distribution? Well, the shape would still be approximately normal. The center would still be the same at 70, but it would be less varied because that standard deviation now would be zero point 0.9 over the square root of 40 instead of over the square root of 10. So now the new spread, the new standard deviation is just 0.1423. All right, so there was your normal model and sampling distribution practice problem. And so I hope you were able to follow all those different changes in the standard deviation based on what was being asked for.